Greetings and salutations, ladies and gentlemen. We are the Loop Troop. Let us first introduce ourselves. I'm Vedika.
I'm Adrin.
And I'm Unnati.
Well, do you just have those days where you're stuck in between? You know, I have my physics finals next month, but come on, I just really want to have fun. Torn between responsibilities and just living life a little? Well, wait no further, because we have the perfect idea.
Yeah, we really got the best of both worlds.
But what is it?
Okay, look. Ladies and gentlemen, welcome to the grand opening of the Loops of Doom at this fair. You might think a roller coaster is all about adrenaline and the rush you get from it, but it's so much more than that. It's actually powered by pure, unadulterated physics. So cool.
And our VIP passenger for today, this brave little marble. No engines, no batteries, just the laws of the universe.
That's so cool, isn't it? But, quick question, how will this even help me for my physics exams?
Well, the entire workings of this model is based on classical mechanics theory, where kinetic energy and energy transformation meet hand in hand.
Let's first start with the first section of the roller coaster, which is the vertical height loop.
Sounds cool, isn't it? Well, the explanation behind it is just as cool. Because why? For the marble here to successfully even complete a vertical loop, as in its name, without falling. The tricky part, you know? It must enter the loop with enough speed. Tricky. But in a real track, it has friction, but how can we even replicate that? But, you know, it's fine. Let's work with what we have here. So for the marble to enter with enough speed, it must have friction. So what can we do? The starting hill must always be higher up or larger than the actual loop itself. And what will this contraption create? Well, it does conversion of energy, which is a really magical thing, guys. So when it rolls down here, it's gravitational energy because it's all at a height. And then as it rolls down, it converts it into kinetic energy. Why? Because of speed.
To keep the marble from losing contact with the track and falling off, it must reach a critical speed at the top of the loop. At this exact minimum speed, gravity provides the exact amount of centripetal force needed to make the marble spin in a circle, which means the track doesn't even need to push it.
Well, in simple terms, if the marble speed is higher than its critical speed, well, the marble wins, and it stays firmly packed against the track, moving along. But if it gets slower, gravity wins, and it just falls out of the loop.
Oh, that's sad, isn't it? Well, wait no further. Worry and dig your sadness away, because let's move on to the second loop right here. We recreated our actual corkscrew loop. Fascinating, isn't it? We know. Well, this is a multitasking marble at its peak, because it uses the same centripetal force to turn the marble completely upside down, without falling of course, while simultaneously steering it down a sharp path.
Well, we can't just call it twisty. What's actually happening here, guys?
In boring textbook terms, it's known as a 3D helical path. But in fun terms, it's known as a particle accelerator for adrenaline.
That's absolutely correct. At the peak of this roller coaster, where the marble is completely powerless, the marble turns upside down and a thrilling physics battle takes place. So, the marble's own inertia wants to move forward, but gravity wants to pull it down to the earth. So, what happens? Well, its centripetal force, or centrifugal, turns it upside down and makes an inward force overpowering gravity, pinning the marble safely in place along the track for a spectacular inversion.
That was cool, truly. Well, don't leave your seats just yet, because we have the best for the last. Isn't that right, Adrian? Yeah, what is this?
You're absolutely right. Now, last but not the least, we have the infamous snake loop.
Sounds scary.
Well, guys, don't fear, okay? Fear not, everyone. So, the flying snake drive is an incredible complex inversion that flips the runners upside down, followed by a diving twist, which spins the train down backwards.
Well, that's right. So, instead of going straight over, the snake loop forces the marble to climb up vertically and then twist a good 180 degrees sideways at its absolute peak you can see right here. And then it dives straight downwards.
Okay, well, that sounds like that could give me an adrenaline rush. But what do I do if this comes in my exam? How do I explain it?
Well, look, it's pretty simple. At the very top of the snake's head, the marble experiences a moment of zero g-force, weightlessness, as its upward momentum perfectly balances out gravity, finally winning against the battle with gravity. And while it's floating in the split-second sweet spot, well, the track forces a rapid lateral roll, transforming that forward energy into a slithering, spinning twist before gravity yanks it back down into a thrilling tailspin drive.
In pure physics terms, however, a snake loop converts linear kinetic energy into vertical potential energy until gravity and upward inertia momentarily balances at net zero acceleration, where a torque-induced lateral roll instantly redirects the velocity vector into a downward angular dive.
But children, what do we truly understand from this? It's not all about different roller coasters, you know. But what we must actually understand is the core principle of roller coasters in whole. Well, Primarily, it lies on the principles of classic mechanics, which is governed totally by the interplay of energy, forces, and motion. Three key terms for physics. Why? Because a roller coaster doesn't have any engine. I mean, of course, you can't see one, can you? Well, it's essentially just a machine designed to manipulate gravity and inertia on its own through a series of movements.
Well, there you have it. That was the entire physics behind our loops of doom and despair.
So what are you waiting for? The next time we have some science-filled adventure, you will know which roller coaster to take.
That's it, ladies and gentlemen. Thank you.
Thank you.